Yeah, this is the 319K review, and I'm taking questions.
Okay, so fall 2017, problem 1, part E.
Fall 27. Wait. Fall 2017. Problem what?
Problem 1, part B.
P1B. Okay. And I try to do this without. Yeah, fine. I'm going to try to do this without showing you the answer. And so we'll go to the internet. You go to the internet. We will look up fall 2017. Fall 2017. Fall 2017. Okay, you said 1B?
1D.
1D.
Okay, well, that's not the right one.
Okay, well, that's fall 2017. While he's looking, someone else want to ask a question?
Reverse engineering the UART window, like when you see the transfer.
Oh yeah. You want a hard one? Okay, so let's go. Reverse engineer. Do you want a hard one or an easy one?
Hard.
Oh yeah, fine. Okay, so I don't know if I can draw on this. Let's see if it'll let me draw. Fine, let me draw. View. Let me draw. View. 10. Draw. Oh yeah, sure. All right, so the key to a reverse engineer is to know the 4 phases of a UART. It begins in idle phase. Okay? The UART begins in idle phase, which is a high. All right, so if there's a separation between frames, it goes into an idle state. Okay? And then when it begins transmission, it does what? What's the next thing that can happen in a UART transition? A start bit. Has to be a start bit. It can't be anything else. Yeah, question?
Is it always 8 bits that are transmitted?
Okay, that's a great question. He said, is it always 8 bits? The answer is, in 319K, it is always 8 bits. On the TM4C123, you have the option of a 9-bit protocol. On other microcontrollers around the universe, you can go 4 to 15 bits, but 8 bits is what we're going to do in 319K. So it's always going to be 8 bits. So that is the next phase of the information, okay? So, and that's going to be bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, okay? And then the next phase is what? One more phase. Yeah, no, what's your word? Use your words, man. Stop it. And is it high or low? It's always high. Okay? And what comes after the stop bit, by the way? Well, 2 things can come after the stop bit. Well, it's another start bit could happen right there, or an idle. So this is either an idle or a start bit. I don't know. Okay? And so now what I'll do is I'll change colors, and we'll do some, okay? Now, the other thing about this is, what can you tell me about the time between each of these bits? Yeah, but they're the same. Okay, they're the same. They don't have to start at 0. Yeah, wrong color. Just draw red. Oh yeah, that'll work. Okay. The way this is going to be a unique answer is if I give you a problem where the bit widths have a greatest common multiple, by the way. So if you look at the tick marks here, if you look at the tick marks in this problem, bits, yeah. You see, I got a 2 and a 3 and a 4, right? I got a 2, 3, and a 4. You see that? A 2. I got 2 ticks. I've got 3 ticks and I got 4 ticks. What if he was scoundrel and gave you more ticks? Yeah, that's a weird one. What's up with that? That's a multicolor one. Let's go. Yeah, draw. Pencil. Okay, oh, pen. All right, black. Let's go back to black. There we go. All right, so how many ticks are those pulses now? Right? I just doubled it. This is 4. This is a 1, 2, 3, 4, 5, 6. And this is a 1, 2, 3, 4, 5, 6, 7, 8. Right? What's the least common multiple of those 3 numbers? 2. Okay, go to the red ones. All right? The red ones. Okay, I didn't mess up yet. All right? Where it was 2, 3, and 4. What's the least common multiple of 2, 3, and 4? 1. So what's the bit time? 1 red tick or 2 black ticks? Yeah, see how I did that? And once you figure out the ticks, now I can associate it with the top waveform to figure out the bit pattern, which here it's got in reverse order. This one here is a 0. I got 2 1s, and then I have 3 1s, and then I got 4 zeros. All right, so that's a 0x 0e. Okay. I couldn't choose 2 tick marks. I mean, I couldn't choose 2 reds as my multiple because I wouldn't have been able to fit it into the 3. I couldn't choose. So there are other choices, I suppose, that could be 2 frames. I'm not going to be that much of a scoundrel and give you a 2 frame thing. I could be 2 frames, not 1. Yeah, question. Is that enough? Is that who asked the question? Is that what you wanted? Yeah. So the thing that I do is I look for the least common multiple, and that gives me the bit time, right? The least common multiple gives me the bit time. I figure out the bit time, and then I draw my vertical lines such that I don't have a bit flipping in the middle of a bit time.
Right.
It has to be low or high during the entire bit time. And then the baud rates went over that. Yeah, question?
What would your max bandwidth be?
Okay, so we're done with drawing pictures, reverse engineering. Okay, the BMEs out here? Any BMEs in the audience? Okay, did I tell you the project what I did with pacemakers?
You slightly talked about it.
Yeah, what I had to do is I reversed engineered the pacemaker protocol the same sort of way. Yeah, it was a little more complicated, but yeah, it sung like songbirds. Okay, yeah. So that's all right. Let's go on to the next thing. Okay. All right. So what's my next question? Oh, bandwidth. Okay. So what's the definition? Okay. So the question I think you asked is what is bit time? What is baud rate? And what is bandwidth? Okay, so going up here, bit time is the constant time between all the bits. Okay? So this is a constant time. Let's call it T. Okay? Is there any confusion about what that is? All right, so what's the baud rate? It's just 1 over T. That's the total number of bits per, and this is whether the units of this is in seconds, this is in bits per second. And then the bandwidth, okay, that has to do with the information data rate. So the question I think you meant to ask was, what is the relationship between maximum possible bandwidth and baud rate? Okay, so if you were to tack on a second frame right after that, you would have a start bit here. Okay, pack them right together. And so in that case here, for every frame, okay, again, a frame is 10 bits, which includes the start, the 8 data, and the 1 stop. Okay, so the maximum bandwidth here is 8/10. The baud rate, assuming we're in bits per second. If we're in bytes per second, it would be 1/10. The bandwidth equals 1/10 the baud rate. If this is in bits per second, and this is in bytes per second, and just 8 bits per byte. Does that answer your question? All right, so did you figure out which one you wanted?
Yeah, it was problem 2, part D.
Problem 2, okay, so. All right, so. All right, so this is totally on the test, not this exact one, okay? But okay, part 2B. What's the 16-bit hexadecimal representation of
Part
D?
D.
Okay, fine. What a fixed point number has a resolution of what integer do we use? Okay, fine. Okay, so go and I don't know if I can write on this. Probably not. I got minus 3.75. I just got to remember that. All right, let's go over here. The thing you got to remember that will get you all the points with a little bit of thinking is, what is a fixed point number? The value, which has units, by the way. This is going to be in centimeters. This one's in centimeters. Okay, is defined to be some integer, which is the variable part, times a constant. So I just got, minus 3.75 equals I over 4. How's your math? Okay, 15, minus 15. Right, 4 times 3 is 12. 4 times 0.75 is 3. 12 plus 3 is 15. I got the minus sign. Yeah, that's a trivial question. Okay.
On the other question, you were talking about the 1,000 times 38 decimal. Are we going to be able to use a calculator?
No. He said, can I use a calculator? Come on, you need a calculator for 1,000? Really? Okay, no is the answer to your question. No calculator. Yeah.
How did you get the constant?
Well, I was just given to me. Resolution. Yeah. Now I could ask a harder question. Okay. What if I wanted to represent minus 3.5 centimeters using binary fixed point? Right. Well, if I use binary, that's a harder question. And so what I would do in my mind is, if I said, what are my choices here? I could go minus 3.75 equals 15 over 4. I could go minus 3.5 is not exactly equal to 7 over 2. No, the other way around. 7, no, bigger number over 2. No, it's not good. Eraser. Do I have an eraser? I draw. Eraser, I do. Whatever, 30. Okay, I want something divided by 2. That would be 7. Yeah, minus 7. Okay. I could go minus 3.75 is exactly equal to minus 30 over 8. Right. Now what I'm doing in my mind is I'm evaluating the various binary fixed point constants, powers of 2. Right, I could go minus 3.75 equals minus 60 over 16. And all of those, except for divide by 2, are okay. Huh? Are you with me? Yeah. So from a design standpoint, I'm going to choose a power of 2 such that I can represent the values that I need. To answer your question?
Would it always be a power of 2?
Well, a binary fixed point is always a power of 2. Okay. What is a decimal fixed point? What's a decimal fixed point? A power of 10. Could I have a power of 7? Sure. I could have a power of pi. I can do whatever I want.
So in a question like that, you're just looking for what n is?
Well, that particular question, I just looked for, what did I call it? I was looking for I. In that particular question, I gave you n as minus 2.
Right.
And I asked you what I was.
Then your harder question.
The harder question, it's all centered around that. Yeah. All right. So the way we're doing this, though, came in last. I am taping this. It's going to be the most worst YouTube channel I've ever made. And I will, this Word document, if all goes well, I will save it. Okay? But you can see what I'm doing here. I'm basically answering your questions in order as if I had a FIFO cube. So I'm going to put, yeah, you already asked something. You can ask something if nobody else wants to ask anything else. All right? Yeah, you can ask something if nobody else wants to ask anything else. They're glad you're here, by the way, because they need to know the answer, and they're too afraid to ask. So I appreciate your courage. Okay? But welcoming everyone with equal access. Anybody else want to ask something? Yeah.
So, when you're like setting a priority, how exactly does that work? Because I mean, I can just copy it, memorize it, but I don't know what it's actually happening.
I don't know if I'm trying to think. Without showing, and let me go back to this one here. So something really complicated like the priority register, if it's in, yeah, there's one. Okay. All right, so there's a priority register for cystic. This is that same, right? You see it right there? Nested vectored interrupt, sys, underline pri 3. Okay? You with me? That's your exam question. And so let's do an easy question, and that is, how do I set the priority of cystic to a priority equal to 1? Okay? Do you see, how would you describe each of these priority fields? How many bits wide are they? Do you see it? How many bits wide is the priority field? 3. That's a number between 0 and 7. right? 0 is high priority, 7 is low priority. That's just the way it works. And so if I wanted to, and what the crap is E000ED20? Is that memory? No, that's not memory. What is E00? This guy right there. What is E00DED20? It's memory map IO, which is the priority register for SysTick, plus pend SV and debug. Okay, you with me? Okay, so what I want to do is I want to set those 3 bits to 0. Okay, I got to remember, I want 31, 30, and 29 to be 0, 0, 1. I want it, did I say 1? Priority 1? All right. So let's go back over here. Okay, so we're going to set SysTick to priority 1. That's the question I just made up associated with yours. Is that what you kind of had me want me to do? All right. So bits 31, bits 30, and bits 29 need to be 0, 0, 1. Okay, now you guys took 319K. How do you do that? What are the 3 steps to, well, 4 steps actually. I'm going to shorthand this. If I go x equals pri 3, and pri 3, I mean that whole big crap. This whole thing, where'd it go? It's gone. This whole thing, nested, vectored, interrupt, underline SysTick, underline pri 3. Okay? What I got is the original values. Okay? Do you know what the original values of the priority register are? You have no idea what your lab partner did. So in order to set it to a 001, what must I do first? Clear it. Okay? So I'm first going to clear the bits. Okay? Equals x. And I'm being a lazy kind of guy, and so I'm going to take a 0x07, and I'm going to shift it over 29 times. All right, so now I have a 7 in the last 3 bits, and I want to clear it, so I'll complement it. Okay, so I cleared the top 3 bits. Now, if you could figure, oh yeah, what is that? Okay, so that was actually 0, 1, F, 1, 2, 3, 4, 5, 6, 7. All right, eraser, that's what I wanted. Could have done that, but to me this math is easier. And then what I want to do is what? I want to set the 1 into that position, x equals x, or 1 shifted 29 times. Okay. And then I'm not done. One more step. What's the one more step? I need to save it back because x is just some local variable or a register or something. All right. Did I answer your question? The harder question is why in the world would I set it to priority 1? Yeah, if I have multiple interrupts, this one is pretty important. Not the most important, but pretty important. Right, a priority 0 interrupt could interrupt, but a priority 1 through 7 could not. And then each of the guys has its own priority register. Obviously, in this particular exam, I didn't ask you to set the priority for UR. So I don't need you to memorize which register is which. But you should figure out, this should make sense to you right here. This crap right here, that should make sense to you. Okay, question?
Did you get the number 29?
Okay, yeah, right there. You see 31? Right, see right there in the, okay, right? I don't know if I can, right there, this? See it?
Yeah, but isn't 7 3 bits, so if you put it 29?
Yeah, it's going to fill up the bottom 3 bits, the top 3 bits.
Okay,
Yeah. I think I did that right. I did it right enough for an exam. Okay, so if you like put in 28 or something, whatever, I won't argue too much. You should understand that what I'm trying to do is set that field. Yeah. Yeah, great. Fine. I guess I'm going around the loop again. Sure.
Should be quick. So if you're trying to like create a structure, oftentimes you'll put like type def afterwards to create a new type.
Yep.
And I was just wondering, like, couldn't you just like
Yes, of course.
just declare the type after the structure?
Of course. Of course. Oh, there we go. I can't do this. All right, so I want to. So there are. Let me open a. Try not to show you. I don't think I have any exam questions here. No, that's somebody's Space Invaders. That'll work. Space Invaders. So the question, where is my space? Okay, no, that's the starter code. I don't want the starter code. Let's open something with a Space Invader. Yeah. There we go. Okay. All right. So the approach to creating a type def, creating a structure, there's lots of ways. Okay, this is one way. We create a struct sprite without any underlines. This thing here isn't anything. Doesn't create memory, it doesn't create a type, it just creates a structure. Okay? And it's not down here until I create the sprite type. Okay? Now, it turns out I don't actually have to create a type. Okay? Here's this code would have compiled. So if I wanted to create multiple enemies, I don't need the type. It's just quicker, it's much, type def, no. Type def, that was struct straight, that one, sorry. That would have worked. Huh? Struct sprite, yeah, no, struct sprite. I didn't need the type def, it's just the type def makes it easier. The other way is I didn't actually need the struct. I could have type defed it up here. And I don't need this now. And then down here, I put the sprite type.
So if you want to put the sprite type at the bottom like that, you'd have to put type def at the top.
At the top, yeah, because you want it to be a type def. Now, we didn't do this with the finite state machine, is because in the finite state machine, we needed pointers to itself. So I needed, but okay, did I do something wrong here? I don't know. I might have missed something. What did I do? Build? I don't know. But there are 3 different ways to make structures. Oh, when you get to 312, your instructor will do it one way or another. On the exam, use an underlying T when you meant it to be a type def, and I'll figure out what you meant.
What do you mean though that you can't use it to, like, you need it for pointers, so you can't use a type def?
Okay, just so that I don't get wrong. Let me make sure this compiles. I could. Yeah, I've got a mistake here somehow. I'm gonna have a type def sprite. Oh, type def. Yeah, you don't have a sprite. Yeah, you don't put the sprite there. Okay, so that's the mistake. Nope, still wrong. Type def space. I don't know. Type def struct. I need the struct. There we go. There we go. All right, so I get the luxury of the compiler. You do not in this exam, but I promise you stupid syntax errors like I just made there are not going to kill you. Right? All right, so this is a perfectly legit way to make a, all right? Let me open the traffic light controller and you'll see why I had to do it the other way. Table traffic, I want the pointer traffic light. Finite state machine, stepper, pointer traffic light, there we go. Now I don't know if you've studied this one, but this finite state machine here is a finite state machine which has states which are pointers and not. If I tried to type def this, I would not be able to write line 49. Line 49 would be unwritable with that other syntax.
Why is that?
Because there's nothing you have not yet defined the pointer. You haven't defined the type until you've got there. It just doesn't compile.
Okay.
And it would compile on the exam. It would compile on the exam because I don't care, but it would not compile in real life. All right, so while we're talking about structs, okay, I've shown you two structs so far. In what way are these structs different? Okay, just look at this struct here, okay, and let me go back to the other one. If I open back to this other one, and I'm gonna undo the mistakes, the change I did before. This is gonna be, I'm gonna take this guy out, sprite. This guy goes away. This guy comes back. Okay, this is where it was before. Okay, I want you to look at these two structs, and in what way are they different, and in what way are they the same? Okay, yeah.
One is pointer, one is index.
Fair enough. Yeah, the one is a pointer, one is index. That's actually a correct statement. That's not the. Where is this? Where is enemy located? If you were to put your finger on enemy, where is it defined? Is it in RAM, on the stack, in a register, or in ROM? In RAM. You see how and I want you to look at the other type def to see how I got the other one to go into ROM. Okay, you with me? Okay, and I want you to focus your line on this guy right there. You with me? I want you to focus right there on this line. Okay, and it's how did I get this struct? Yeah, you see the const right there? That placed this finite state machine into ROM. Okay? That was the point I wanted. Any questions about structs while I'm looking at structs? Well, I got structs open here. Let me talk about structs, yeah.
So what is line 50? What is it?
Pick a 50.
Yeah.
Okay, so he's asking what's a type. All right, that's what he's asking. Okay, so let me ask you, what types do you know about? If I can figure out how to get, I'll just type it here and it'll be fine. Give me an example of a type. No, I don't want. I want a type. I don't want it enumerated. I don't want an enumeration. I want a type. Somebody help them. But integers not. There's no integer types. And not in this compiler. There's no integer. All right? Okay, yeah, here we go. Thanks. Int 8 underline t. Okay, that's a type. Okay? What can you do with a type? Make crap, right? Z. What goes before a variable definition? A type. What goes before a function definition? A type. Okay? What goes before a parameter definition? A type. Okay? What goes before a pointer definition? A pointer. I want to make a pointer. What goes before a pointer definition? A type. Okay? And so the question that you asked is, what is line 30? I just created a new type, such that if in this particular example, I didn't use the underlying T. It was back when I was a young man, a long time ago. Every time I use STYP, I can use it before any of those things that we talked about. I can use it before a variable, like right here, I used it before this array definition. Okay? So before an array definition, I have to give the type. There are 4 things of type S-type, state type.
So STY
Is a type. So type def is the type def is the first thing in a type definition. Whatever's at the end is the name of the type, and the crap in the middle is whatever it means. You're gonna create a type based on other things. I could, if I wanted to, create. Why would I do this? Okay, do type def. U int 32 underline t. U int 32. What's the point of that? It's just faster to type now. Right? Somebody wrote code that has every unsigned 32-bit numbers with that type. Okay. You'll see that when you get to C++. That's the type. That's the typical typecast for an unsigned 32-bit number. But I can reassign. How about this one? Cool. Check this one out. Okay. Whatever. What type is this? Type def bool int. The other way around. Eraser. Quick. Eraser. Int bool. It's made a Boolean type, but when it actually executes, it'll be an unsigned. It'll be a signed integer. Any other questions about typing? Yeah.
So since the system we were using is 32-bit addresses, does that mean our pointers are always going to have to be a 32-bit type?
Oh, great question. Great question. Obviously not, right? So it's sort of a loaded question. Let me see if I can figure out how to get to the end. Go to, oh no, I want to, oh yeah, maybe I'm going to view. Draft. Here we go. No, that's not it. Print line. Ooh, that's fine. X. B. There we go. Close enough. Yeah. You can now type the end. Okay, good. So whenever you have a uint 16 underline t, okay, translate that to assembly language for me.
You're allocated to.
No, it's a pointer. No, it's always a 4. Regardless of what's on this side of the star, all pointers are 32-bit numbers. Okay? Let's do another one. X equals star P. What opcode is going to be generated when I dereference that pointer? Not LDR. LDRH. Now there's going to be an LDR up here where I do R0 equals P. But when I dereference it, I'm going to use an LDRH. Okay? And so the opcode here matches the type. But the pointer is always 32 bits. Did that answer your question? Yeah. Okay, good. I'm going around the room, and so if you haven't, come on. There's somebody who hasn't asked the question yet. Come on down.
How do you know when you have to use const?
Oh, okay. So he said, he just said the word const, okay? And so what I want to do is make sure you understand what it means, okay? And in the context of 319K, it'll mean two things. But in the rest of your life, it will mean one thing. Does not or cannot change. It means just what it means in English. So when you write code and you have something that cannot change, if I have something that cannot change, okay? It cannot change. I better tell you what it is. Because if you don't tell me what it is, it's going to be a 0. And so I'll set it to something. And then if it cannot change, I'll tell the compiler, anybody who tries to change B is not compiling. Okay? So, but in terms of 319K, what that means is it goes in ROM, because we got a lot of ROM. Okay, so in 319K, it'll put B in ROM. Okay, the other place you're going to see const in 319K or in the rest of your world is in a parameter. No, eraser, and draw. Eraser. Okay? And this is not going to put C into ROM. C is in R0. But what it is going to mean is the program cannot change it. Whatever that parameter is in C cannot be changed. Up here, if you wrote B equals 6, what would happen? It would not compile. Down here, if I say C equals C plus 1, what's going to happen? It's not going to compile. But I can do, I can look at C, I just can't change it. That's the definition of const. You can look at it, but you can't change it. Now the tricky one, let me just do one tricky one here for you. Yeah. Let me do one tricky one. And that is this. Where's the pointer? It's in RAM. Pointer's in RAM. The pointer is going to point to something that doesn't change. Okay? So if I do something like x equals star pt, I am dereferencing the pointer, reading its contents. This is allowed. But if I do star pt equals 6, I'm trying to write into ROM. This can't happen. Okay? Did I answer your question about const? All right, opening question. Yeah, question.
Similarly, how is data allocated for a static or a volatile?
Okay, so don't ask me 2 questions.
Okay.
Ask me 1 question. Let's do statics. Okay. This is on the test, by the way, so you might as well pay attention. In 319K, we defined variables with the following parameters, with the following characteristics. The first was this issue of scope, okay? And when I say scope, I mean everywhere, no unrestricted. And that is anywhere, not any time, but anywhere, anywhere. It's, and then we're going to have restricted, reduced, somewhere. Restricted. Okay, somewhere. Not everywhere, somewhere. We're going to reduce the scope in when can it be accessed, or who can access. That's what I mean by scope. All right? And then the other aspect is allocation. And in the context of 319K, or in all programming, we could have temporary or permanent. Okay. Permanent means it always exists. I mean, you hit the compile button, it assigned a space in somewhere in memory, and then until you erase the ROM or throw it in the trash, that variable has permanence that exists forever. Whereas temporary means dynamically we're going to make it alive. Alive, I can't spell alive. Alive. We're going to make it alive, we're going to use it, and then we're going to discard it, destroy it. Dynamically. So here are the things you already know. What's a local variable in the context of this plot? A local variable. Which one is it? This one. This is a local. Okay. Where are locals allocated? Okay, he said it really fast. Say it again slower. That was the right answer. Registers or the stack are both places you can temporarily create a variable, use it for a while, and then destroy it. Now, you're not blowing up the registers. You're just reusing the register for somebody else, right? And the same thing with the stack. You're not destroying the memory. You're just popping the crap off in there, okay? Where are globals? Which box? Unrestricted permanent access. Okay, with me? That's what a global is. It can be accessed anywhere, anyhow. So, for instance, if I create a variable here, if I create a variable here outside the function, any scoundrel in the world, well, in your program space, can go extern int x and get access to that same variable. That's what I mean by unrestricted. Okay? It's unrestricted. Yeah, question?
How does labeling a integer or variable const or hash define impact where it is on this?
Const. Okay, no. Const has other than the fact you don't have const. You generally don't have. Oh, sure, no, it wouldn't. You can do all of this with something that's temporary. Yeah, I could put const in front of this, and it would still be a global. Const doesn't affect. Well, I don't know if const. I have a temporarily allocated constant. Sure, I could. Yeah, I could do that. I could put a constant in a register.
So the whole purpose of const is
No, we already did const. We're talking about statics. Const doesn't change its allocation, or it changes it from RAM to ROM, but it doesn't change it from permanent to temporary. Doesn't change it from permanent to temporary. It doesn't restrict its scope. Const doesn't change the scope or whether it's temporary allocation. We got one more, right? That's the whole reason why we're here. And statics are restricted permanent. Now, some people call them static locals and static globals. Some people use two types of statics, and you'll see it when I define it. Some people call these automatic, by the way. That's the other. We don't do it in 319K, but they might do it in 312. So if I were to go static int y, and then if I have some sort of function, where is y located? Permanent or temporary? Permanent. And the only place you could put it is RAM, right? Because it's not a constant, it's a variable. Okay? What is its scope? What's the scope of y? This file. It's restricted. You cannot do extern int y. This would not compile. It's private. It's reduced scope. Okay. Where is z located? Permanent or temporary? Permanent. That's what a static is. Permanent. So where is it? In RAM. Okay. Now the only tricky part is when is it initialized? Once. Turns out the first time through or during reset, it'll set z equal to 5, and all the other times through it will not reinitialize z equal to 5. That's just the way they work. Sorry. Yeah, question?
So then what's the purpose of doing a local static? Would that mean that you can access it wherever in the file as well?
Okay, no. I do. So she sort of jumped ahead. Some people call this a static global. Some people call this a static local. Okay. And I don't care what you call it. What's the purpose of a static? What's the purpose of reducing scope? Yeah, it reduces complexity. Okay? So the purpose of statics is to reduce complexity. What's the purpose of having a permanent variable? Yeah, you can pay attention. You know what happened last time. You know what happened last time. So, for instance, what if I did this? Static, spell it right, John. Static uint 32 underline t underline c equals 0. And I go C++.
Next time it's involved with
Okay, what is C going to mean? How many times this function has been called? Right, so you're a scoundrel, you're trying to make a lot of money, and then you go if C equals greater than 1,000, then you do a blow up the machine. So it works just past the warranty and then destroys itself. I mean, it's a little bit stupid, but yeah. Yeah, question.
Will these static lines execute after the first time?
I can't hear you. Say it again, Laura.
Will the static line?
Well, the variable's permanent. The variable's permanent. It gets allocated at compile time. It gets defined at compile time. The Z equals 5 or the C equals 0 is executed once. So I guess you're right. Yeah, those lines aren't executed. The variable exists. Oh, what is the scope of Z and C, by the way? Just the function. Okay? Just the function. All right. Okay, so I know you've got lots of questions. Yeah, I haven't heard one from you yet.
So what we normally do, like in Lab 5 for the system integer, is that we put the real load value, we cleared the current resistor, and then we said, well, bit 16 of the current. So for us to know that it has not yet came to 0, like it hasn't finished counting.
Are you talking about interrupts or busy wait?
The timer of this.
No, the timer, but we use statistic for two things, for time delays and for interrupts.
Well, yeah, for interrupts.
Interrupts. Okay, so you want to use SysTick for interrupts.
In assembly and in exam, what you did is you just put like the full number in a variable, and then you start as a
Okay, can I ask you to like pick an exam number, or I can say, let me ask the rest of the class while you're looking up something. Okay, how often is the SysTick interrupt? Do you want me to do frequency or period? Pick one. Frequency. What is the SysTick frequency? Assuming I'm going to generate interrupts, what two things will affect the SysTick interrupt frequency? The reload and the bus clock. Okay, so it goes to reload, counts down to 0 on interrupts. Okay, and so the SysTick frequency is going to be the bus frequency divided by reload plus 1. Okay, is that clear? And obviously the period is what? SysTick period, the time between interrupts. Is what? Reciprocal. What did your 10th grade teacher tell you to do? The most important thing you learned in 10th grade? Dimensional analysis. Don't get upside down with your upside downing by getting, frequency is in hertz, period is in seconds, and obviously that's why it's flipped. All right. I will, now I'm listening to you.
Yeah, so it's the number 3 of the exam that you were doing.
All right, how do you like that? I'm so lucky. Okay. Oh, hold on. Let the rest of the class get aboard here. Question 3. Question 3. All right. So where? So right there in the net, this first box is the thing I just did, and that was you're going to set the reload equal to, right? The reload.
Yeah, but in the last one, the SysTick number, there's so it is. What we normally do is we check the 16th bit of the current.
No, you don't. You don't check nothing. The 16th bit of current causes the interrupt.
That's the flag.
Yeah, but that's with interrupts, you don't check the 16th bit. The 16th bit, the count bit, caused the interrupt. Yeah, when you see here, no backward jumps, man. So in here, this is where I'm gonna put that static int count equals 0 when it gets to 36100. I'm gonna flip the counter and flip the output and make it go back to 0. Did I answer your question? Yeah. So it's, but yeah. So yeah, there's the question that we started off with. You got to read it. You got to clear the top 3 bits. You got to set the top 3 bits and store it back. But I've obviously already read it for you, and I've already stored it. So in this case here, you're going to AND it, clear the top 3 bits, OR it with the priority 1, and it will store back. And right there's a 7. All right. Question? Yeah. Okay. I don't know. I don't know who's asked. You've asked the question before? No. I'm just going to kind of do. No, fine. I'm not doing them in first come first serve. I'm doing them in priority order. Okay. If your bid is not yet set, you get priority. Okay. All right. What's your question?
So when we first learned about the AAPCS rules, we learned that we should push registers R4 to R11.
Okay.
And then when looking at one of the exams, it said which registers should you not push, and it said those exact registers.
Well, then it's a typo. Okay, so ARM architecture procedure call standard. ARM architecture. And I don't know the context of the question, but if you are writing a routine, you have to, if you want to use R4 through R11 or the link register, you need to save them. Now the interrupts don't save them.
Oh yeah.
Okay, so answer your own question. Okay, if I write this function, cystic handler. Why did the hardware not push these registers? Well, push this one, but why didn't it push those? Because the compiler, when you write code, if it wants R4, it'll push it. And you don't have to push it twice. If it wants to use R2, if this handler wants to use R2, would it push it? No. And so the hardware will push it. Okay, so if I'm using a register and it's an interrupt servicing, somebody better push it. So with interrupts, R0 through R3 and R12 are pushed in hardware. And then R4 through R11 are pushed by the software, if needed. Okay? And that's the answer why the hardware, that's why the hardware pushes R0 through R3 and R12. And if the software wants to use it, it'll save and restore 4 through 11. Yeah, sure. Yeah, so let's do cystic. Okay, the current goes 4, 3, 2, 1, 0, and then it goes back to whatever it is before, 79,999, 79,998. Okay, that's cystic rolling along. Okay, what happens when it goes between 1 to 0? Yeah, the flag, current, not current, count is set. That's bit 16. Okay? Assuming the I bit is 0, okay, and assuming the control register's got a 7 in it, it's armed, and the I bit's 0. Where's the I bit? Where's I? What is I? What is I? The global interrupt mask bit. Okay, so 0 means it's unmasked. Okay? If assuming that these three conditions are true, it's armed, it's enabled, and it's triggered. Okay? Arm, enable, trigger. An interrupt will happen. Just will. That's the way it works. And what are the steps? It will finish the instruction. And then it will push R0, R1, R2, there's 8 of them, R3, R12, link register, program counter, and the program status word, which has the carry bit, the N bit, the Z bit, and the V bit. Okay? Program status word. 8 registers. There's where it's pushing it, by the way. That's the answer to your question. It just does it. It's not executing code. And then it's going to set the program counter equal to the vector address. That's the address of the interrupt service routine. It sets the link register equal to 0xFFFFF, 7 of them. 9, 7, one of those. 9. Now, what else does it do? Done. So that's software. It's executing instruction. This is software again. This is the first line of the ISR. So those steps there occur automatically in hardware. You're not executing any code which sets the link register to FFFF9. It's set by the processor as it does the context switch. Okay. While you're here asking a hard question, what does the branch link instruction, branch X, what's that instruction do in the context of interrupts? What's in the link register? No. Oh yeah, it's not. It's not. What's in there? 0xFFFFF, 7 of them, 9. What happens if I try to chunk FFFFF9 into the program counter? Doesn't do it. What does it do? What do you want it to do, man? Yeah, but how do I going to go back? What's on the stack that tells me where I was? All this stuff up here. It's going to pop. This instruction here will pop R0, R1, R2, R3, R12, link register, program counter, and the program status word. Then it goes. That's how it gets back. All right. I have another question from. Okay, go.
I'm looking at fall 2012, question 7.
Yeah, the further you go back, it's more likely that it's relevant, but you asked nicely and then we'll look. Okay. Yeah, come back here. Fall 2012. All right. Okay, so which fall 2012, that one. All right, what question? Oh, yeah, that's a good one. I can ask that. Sure. Just Ohm's law. Okay. All right, this is the question. What is your what is your question for me?
So when like solving it, like I don't get the final.
Okay, so let me help everyone by reminding you the rules, because even if I don't ask this exact same question, I can ask a similar question. Okay, so how many sources do I have? How many input sources do I have? I have 2 input sources. Bit 0 and bit 1. How do I solve a linear system? It's linear because it's Ohm's law. How do I solve a linear system if I have 2 inputs? What law allows me to superimpose the final solution based on individual easy questions? The law of what? What law allows me to superimpose one solution with another solution? Law of superposition. Okay, fine. You're speaking quietly and I didn't hear it. So what you're going to see is I'm going to solve them one at a time. And so I'm going to, and the rule is, if I'm going to put, how many volts did I have? How many volts did I have coming in? 3 volts. Okay, I'm just making the math easy for myself here. Okay. So if this is 3 volts, what do I do to my other, my other source? What's the law of superposition say? If I'm going to look at one at a time, what do I do with the other source? Set it to 0 volts. Not open it, set it to 0 volts. So I'm going to just I didn't actually ground it, I'm just going to think about it being ground. Okay, so what's my next rule I need is, how do I combine resistors? What do I do if I see 2 resistors in parallel? There's a rule. Because I'm looking at this part right there. Yeah, there's a rule, 1 over plus, if I got 2 resistors and I want to know the effective resistance of the 2 in parallel, I'll do that. Well, this is easy because I got 1 over, 1 over, 1 over, 1 over. And so what is the impedance of 2R in parallel with another 2R? This is just R. Whatever R is. Okay? So I have this guy, 2R, R, ground. And that guy's 2R, 3 volts. Okay, so I need another one. What if the 2 resistors are in series with each other? What do I do? Those 2 resistors are in series. I add them. Okay? So these 2 become 2R. Okay? And then I'm going to flip this one. There's the 2R. 2R. I'm going to combine these 2. Those 2 are in what topological order? Are those the 2 that I've circled? No, they're not. They're in parallel. So they have an impedance of 1R. And so the question is, how much current is flowing right here? You with me? So I need another one. What's the famous rule that relates voltage and current across a resistor? Ohm's law. Okay, so this current here, this current, let's call it I0. This current here is 3 volts over 2R. Okay. But now, that current is this current. So what famous rule allows me to sum the currents around the loop on a point? I'm going to use Kirchhoff's current law, and the sum around this node is got to be 0. So this current comes in, some of it goes left, some of it goes right. How much? You see it? This guy's going to come up here. Some of it's going to go that way, some of it's going to go this way. Divides in half. Okay? And then if I go over here, this is 1/2 I0. How much of it goes this way and how much it goes that way? The answer is 1/4 I0 goes that way. And then I'll do the other one and combine them up. So this is a little bit complicated. Kids don't do very well on it, but I will promise you the things that I am going to ask you is for you to understand the law of superposition, which is to take the signals one at a time, and all the other voltages we're going to short to 0, to ground. Okay? You're going to have to be able to combine resistors in parallel and in series. You're going to have to see Kirchhoff's current law and Kirchhoff's voltage law in order to solve the problems. Yeah, and this is called an R2R ladder. Some of you have built 8-bit R2R ladders in your yeah. It's got feature. It's a very popular way to make a DAC. Yeah. Question.
So do we need to know how to construct an R2R ladder?
No.
And all the logic?
No. No. This is what you need to know. You need to know how to analyze one. That you need to know. Okay?
Maybe talk about.
I can't hear you. Anybody want to ask a question? Because we're almost out of time. Yes, you may. But hold on. Going once. What's your question?
FIFOs implementation.
Oh yeah, FIFOs. Okay, how do I do this without giving you the answer to the test? Now let me be first. It doesn't take a rocket scientist. Has anybody looked at any old exams? Do I ever ask a FIFO? Yes. Do I ever not ask a FIFO? No. Okay, so what do you want to know?
Everything about.
I can't do that. It's just on time to everything about it.
How do you initialize?
Okay, so I can't answer that. But what do you do during initializing? No. I don't want you to parrot the answer. I promise you the answer to your exam is not something you're going to memorize. I promise that. Because, what kind of teacher would I be if I just wanted you to memorize? Okay? But let's generalize all the FIFOs you've ever seen and ask the question, what happens during initialization? You're giving me a particular solution. Yes, so set the 2 indices to 0, set the 2 pointers to the beginning. Those are things you've seen before. But what do they two have in common? Make it empty. Yeah, totally right. Make it empty. I mean, to some extent, it's a little bit circular because I haven't told you what it means to be empty, but we might as well. We're going to define what an empty Q is, and we're going to make it empty. Sometimes we just set size equal to 0, and now it's empty. Sometimes we set the put pointer equal to the get pointer. Sometimes we set the get index to the put index. You were in my office once and said, well, what if I subtract 1 from it? Or what if put pointer points to the oldest? Yeah, you can make it whatever you want, but you're going to define what it means to be empty. Okay? Whether that is, put I equals get I, or equals 0, or put pointer equals get pointer equals the address of the first element of the FIFO, or maybe that means size equals 0. I don't know, whatever it means, I'm going to make it empty. Okay? So there isn't one answer. I don't want you memorizing it. I already did that. All right. Whatever. Okay, okay, draw. All right, so what do you do when you want to put? No. Okay, fine. Okay, good answer. Good. Actually, I should have shut my mouth up. Okay, that was a good idea. Yeah, that's actually a good idea. Yeah, you should probably make sure it's not full. What does it mean to be full? Well, it's just like, what does it mean to be empty? You're going to define what full and empty are. You're going to make sure it's not full. Because if it is full, you're going to return an error. Some FIFOs, if it's full, they'll just wait. Some you get to 312. If it's full, it's going to allocate more space. Not in 319K. Just malloc more space and make the queue bigger. But in this case, if it is full, we're going to throw an error. Right, good answer. So what are we going to do second? Store, yeah, I'm going to store. In a first come, first out way. Such that when you do the get, you get the oldest. And so again, there's lots of ways to store. I could shift the data, I could shift the pointers, I could shift the indices. I could go to the internet and buy myself a hardware FIFO. I could hook it up like the LCD and make a hardware FIFO. That's more of a 445L thing. I can buy hardware chips that implement FIFO. I won't in 319K. But the point is, I'm going to store it into the... And then I'm going to return a true, right? This is going to be a return some sort of success. Now, it's possible that if you want to put, and if it's full, you could loop. You could busy wait on it. You could. Again, you can't store into something that's full. Okay? You got to either return with a failure or go back and wait again. All right, so what's a get? It's going to remove, but what do I got to do first? Check and see if it's empty. Okay. And again, I can do one or two things. I can return a failure. If empty. Or I can loop back busy wait. And assume some sort of interrupt's going to help me out here. Okay? But assuming it's not empty, which one do I do? I'm going to remove the oldest. And return a true. Is that enough of an overview? So, yeah, look at, somebody in your group wrote one of these bad boys in Lab 9, okay? One of the two of you. If it wasn't you, go look at it. If it was you, go look at it. In the book, there's a whole bunch. On the internet, in the old exams, there's even more of a bunch. And that is our, our pleasure when it goes to write a final exam, is to figure out a new way to ask you exactly the same thing so that you didn't memorize it, but you understood the essence. All right, what are we doing? 5 more minutes. Yep, go.
I have a question about like ABC and how it's like a process. Like if you could look at spring 2016, question 7.
Okay, so back. Hold on. Back. Okay, now I'm listening to you. Say it again. Spring 2016. Okay. Which question?
7. Part 1.
7. Okay, question 7, part. Okay, yeah, this was the reverse of the question that somebody asked before. So, I'm sorry, you meant C, or do you mean?
I meant C.
You meant C, okay.
Yeah. So I just had a question.
Hold on, okay, so I'm listening to you. I'm listening to you now.
Okay, I just have a question because like I think it's solved differently in
Yeah,
2015.
well, one of them could be wrong. Okay, let's solve this one and see. The idea here, okay, I got to remember 12-bit, I got to remember 125, and I got to remember 3 volts. All right, with me? I got to remember those 3 things. Say, Control S, final, desktop. All right, desktop review. Okay. Yeah. I don't know. No, there it is. Okay, good. All right, so it was 3 volts. Okay, so an ADD converter has what of its input and what is its output? If I'm looking at a causal relationship of an analog to digital converter, what's on the x-axis and what's on the y-axis? What's the input to an analog to digital converter? Analog or digital? Analog. 0 to 3 volts. Okay? So what's the output? Digital. It's 12 bits. 0 to 4095. Okay. What's the relationship? Linear. Now, if you zoom way in, it's stepied. But if I zoom out at this range, it looks like a straight line. Okay, and so the question asked, oops, crappy drawing, what is it at 1.25 volts? Okay, so it's going to be either, depending upon whether I got a calculator or not, and I don't, so I'm going to do the easier math, because that's the way I roll, okay? 4,096 times 5/4 over 12/4. Oh, it's not that easy. Well, maybe not too bad. It's on a power of 3, whatever. I'm going to have to get out. No, are you with me? I'm going to get all the points by writing this, by the way. Just saying. Yeah, but is that enough of an answer?
Yeah.
Okay. I mean, I'm not saying there are no typos in the solutions, as long as you understand what we're doing.
Could you quickly show how to interface a positive and negative LED with driving.
No, I can do one, not the other. Because I'm not going to ask you the other one. Positive logic, I over 8 milliamps. That's exactly lab 3, by the way. Okay, positive logic LED is exactly lab 3. So we're going to use Kirchhoff's current law. Okay? Kirchhoff's current law tells me what is the relationship between these two currents. They're equal. Kirchhoff's voltage law tells me that the voltage across the resistor plus the voltage across the diode plus the output low voltage, or whatever you want to call this voltage, is equal to what? 5. And this is our ULN 2003B, such that if this is high, this thing goes low to some number, goes low to that. And then I'm just going to use Ohm's law and these two things to calculate the resistance. Now, negative logic driver, so I don't know, it's not on the test, but so I don't, can I not care? Yeah, no, it's just not care. I'll just use a different chip. That's the answer. I'll use a different, I use a chip without the circle in it. Yeah, but I won't ask it on YouTube. But there are chips that look just like it, except the. You remember what you did with pin 9? Yeah, you hooked it up in lab 5. You did. Nope. But I'll let you look it up. You did do lab 5. The other lab 5 is the other place you use this driver. Okay? In two ways, how was lab 5 different than this? That's lab 3. What did I do in lab 5? Yeah, we connected up. What's inside of 9 was a diode. And I got to get it going the right direction. Sorry. Yeah. Okay. So on the ULN chip, it's the same. Sorry for being stupid here. Let me erase. How else was it different? What way are these two? This is a pin, right? Is this an output pin or an input pin? Is that an output pin or an input pin in lab 3? Output, you're turning the light on and off. In lab 5, is this an output pin or an input pin? Which way is the data going? Which way is the information flowing in the stepper motor? Out. It's another output pin. Right? So that part's the same. We got 5 volts, we got 5 volts. Those are the same. But what else is different? You had a coil here. What'd you do with it? You had 5 of them, by the way. Drawing the circuit.
With
No, the question is, when you did Lab 5, did you use any resistors at all in your circuit for Lab 5? I mean, maybe you've had switches, but for the stepper motor, did you have any resistors? No. So the thing that's different is there's no resistor here. You put what voltage is across the coil when it's on? What's this voltage? Right, if this is 0.5, just like it was up there, this gets 4.5 volts. Now I won't ask you how much current flows because it's actually kind of complicated because it's not a resistor. Current can actually flow the other direction, by the way. Current could go up or down, or it could be 0. But the voltage is 4.5 volts. Okay, here we are. Be nice to each other. Get a good night's sleep. Same things I said at the end of class last week. The priority order of the thing most important to me is what is the most important thing I did this semester when I thought it was really, really important? Which one? No. I meant things that you could possibly be studying today. I heard it. What? Labs. If you don't understand your labs and you get the question wrong, that's on you, man. Okay? What's next? Can I? All right, so I don't, there isn't a next. Okay? You have homework, you have worksheets, and you have lectures. And you have the book. Okay? I don't know. I can't necessarily place it. And you got old exams. If you just do old exams, you're going to miss something because I don't know. Because I don't think I've asked a question on your exam I've ever asked before. If you find yourself sort of copying something you've memorized, you probably missed it. Okay? All right. Well, enjoy, get a good night's sleep, eat well, and we will see you tomorrow.